So this is the carbon-13 NMR. Carbon-13 NMR is slightly different from proton NMR. First of all, the sensitivity of the carbon-13 NMR is very low comparing with the proton NMR, because if you think about like methane molecule, 100% or almost 100% of hydrogen atom in the methane is hydrogen atom, not deuterium, not tritium, right? Because the natural abundance of simple hydrogen atom, I mean the isotope 1, is about 99 point something, right? So if we investigate the molecule of methane, we can see all the molecules containing hydrogen atom, the normal isotope. But carbon-13, it is only about 1%. That means if we have 100 molecules of methane, there's only one molecule that can give you the NMR signal, because it's only one molecule containing carbon-13, right? So the sensitivity is low because not every molecule contains carbon-13. It is only 1%. And secondly, that's the drawback, right? But the advantage of carbon-13 NMR is the resolution. Because as you know, from proton NMR, we have several kinds of proton in the molecule, in different kind of environment, right? Such as carbon sp3 carbon connecting with hydrogen, it appeared at about 1 ppm, and at another end, like carboxylic acid, appeared at about 10 something, 12 ppm, 11 ppm. So the windows is about just 10, 12 ppm wide. But for carbon-13 NMR, it's about 20 times, right? So in the picture over here, as you can see, the upper graph is the chemical shift of proton NMR, but the bottom graph here is the chemical shift of carbon-13 NMR. So the carbonyl appeared around 200 ppm, and the alkane appeared about 10 ppm. So the windows, the observation windows for carbon-13 is about 20 times greater than proton NMR. So the resolution is better as well. So for proton NMR, as you saw some of the examples, some peaks overlapped, right? But carbon-13 NMR never overlapped because the resolution is so great, right? Even though you have alkanes, long chain of alkane, you can count the number of carbon in the proton in carbon-13 NMR, right? By counting the number of signals, it reflects the carbon, the number of carbon, because they are just so different from each other, right? And this is why we trying to do the carbon-13 NMR, even though the sensitivity is very low, because the resolution is very great, and because it's very low sensitivity, as I said. So if we let it to be coupled, right, then the peak height is decreased by the coupling, right? So it is this doublet. The height of the peak reduced by 50% into 1:1 ratio, and for the triplet 1:2:1 ratio, the peak height will be reduced to be 25, 50, and 25% from the original, right? So we normally do not let the carbon-13 to be coupled with something else. First of all, carbon-13 will not coupled with the carbon-13, will not coupled with the next carbon. It's different from proton NMR, right? Because in proton NMR, the proton, the observing proton coupled with the neighboring proton, even though there are three chemical bonding far apart from each other, right? We have about 3 chemical bond separation between two protons. But carbon, because as I say, as you can see, carbon-13 is about 1%. So let's say that if you have ethane molecule, C2H6, right? If The C2H6 100 molecules contains only 1% carbon, right? So the chance of another carbon next to him is carbon 13 is even lower than this, right? Because the percent will drop down to 0.01% by calculation. So carbon 13 will not never coupled with the carbon nearby, but it coupled with proton instead, right? So if your carbon surrounded by only carbon, right, bounded with 4 bonds with carbon, so it will be appeared as singlet. But if your carbon connects to one hydrogen, right, and the rest 3 chemical bonding is connecting with carbon, so it will be coupled with that hydrogen and appeared as doublet, right? And if your carbon connecting with 2 hydrogen atom, it will be triplet, right? That's the example. But as I said, if it is coupled, right, so everything reduced, the signal peak height is reduced, right? And because the sensitivity is very low here, so if the peak height is reduced down, then it would be mixed with the noise, right? And we cannot show that is the signal, the actual signal, or the noise, right? So we normally decoupled. Decoupled means that we just like excite every hydrogen atom to the excited state level. So there is only one type of hydrogen, right? So your carbon appeared as singlet always. So this kind of thing is called the decoupled experiment. So instead of let it coupled with hydrogen atom in different energy state, ground or excited state, no? So we just decoupled by excite every hydrogen atom up, okay? And another thing that's very important here is the half-life and excited state. So normally, when we do the NMR experiment, we use radio frequency source, right, to excite your carbon to the excited state. When it go back down, it release the energy, and we collect that, right? And yeah, because it's very low, right? Because it's only 1%. So just only single time excitation, you will have very weak signal here. So you need to repeatedly excite it, okay, for several times, maybe 100 times, to increase the intensity of the signal to 100 times as well, right? But if we excite carbon, right, up to the excited state, when it go back down, we collect the data, right? But it takes time to let your carbon go back down to the ground state. It's very long time. So normally we will not wait until every carbon atoms come back down to the ground state and then re-excite for the second time. We may just let it come back down for several 1-2 seconds and then excite it again, right? So only that, right? Only that 1 or 2 seconds. What happened is different type of carbon here, from primary carbon, secondary carbon, tertiary carbon, and quaternary carbon. It takes different time to come back to the original state, to the ground state. The methyl group, primary carbon, come back down very fast. So when we excite it again, almost every carbon atom is come back down already, give us the signal already, so we can excite it and collect it again and again. But quaternary, it will hang up in the excited state for a very long time. So during the NMR time scale, I mean 1 or 2 relaxation timing, it come back down just about 10%, 20%, thing like that. So when you excite, so the data collected is about just 10% of the peak height, comparing with the methyl group or primary carbon. So that means we cannot, doing the peak area integration for carbon, unlike hydrogen atom, because hydrogen atom we do the peak integration, right, to find out the number of hydrogen, the ratio of the hydrogen in the molecules. But carbon-13, you cannot do that because each type of carbon gives you different heights of the peak. Okay, so these are the things that differ from proton NMR, right? So roughly, what you have to use is this graph, right, that I summarized here. So the position of carbon is exactly the same as proton NMR, but you have to multiply it, the chemical shift from with about 15 to 20 units. Like aldehyde, as you can see, it normally appeared at about 9 to 10. So the carbonyl group, right? So it's in the same environment. That carbonyl group appeared, you multiplied it with about 15 to 20. So as you can see, it appeared at about 160 to 200 ppm. That's the carbonyl signal. Or the alkane. The alkane normally in proton NMR appeared at 1 ppm. So for this, appeared at about 15 to 20 or 30 ppm. So approximately. So it's quite easy. Okay. So that's all about the summation of carbon-13 NMR. Now we're going to look at some practice exercises. So see you again in the next video.